This work is a part of a doctoral thesis of Selma Shabar and is developed in collaboration with Abdelrahman Habbal from University of Nice and El Mahdi El Garmah from ERA School in Marrakesh. This work is supported by the CNRSC through a research program, Al-Khwarizmi, and the second part of this work will be developed in collaboration with oncologists from Mohammed VI University. I will follow in this talk the next outline. After a brief introduction, I will present an optimization formulation using a PDE model, and then a numerical resolution with some numerical results. And I will present a hybrid model using NetLogo. And I will talk about sensitivity of the model with respect to some parameters. Following the World Health Organization, cancer is the second leading cause of death in the world. Cancer caused nearly 10 million deaths in the world in 2020, and 1 in 6 deaths is due to cancer in the world. Hence, the interest of scientists, and in particular, mathematicians in this disease. How we can differentiate diseased cells from healthy ones? Healthy cells divide and die in controlled process to ensure the proper functioning of the organ. Diseased cells are divided in an excessive and anarchic way, and then causes a malignant tumor. In order to proliferate, the cells need nutrients. Insufficient nutrients can cause emergence of quiescent cells, and an extended period of quiescence lead to a cell's necrosis. The tumor tissue consists of healthy cells, which are the normal cells, proliferative cells, which are the cancer cells or cancerous cells, and the quiescent cells, and the necrotic cells, which are the dead cells. In this work, we will neglect the quiescent state, and we consider as only nutrient the oxygen. The tumor growth is modeled with respect to different levels: the cell density evolution, and we are interested by the healthy cells, proliferative one and necrotic one, and we are also interested by the geometric progression of the tumor, and then we have to search about the free boundary, which is a contour of a tumor. Let's be omega the tumor domain at a time t, and we denote by D, a fixed domain which contain the tumor, and we denote by lambda mitosis the right of mitosis, and by mu this the right of the death, or the right of necrosis. And C denotes the oxygen concentration in the tissue, and C thresh denotes the oxygen threshold below which the cells are short in oxygen and became necrotic. The oxygen is diffused through the tumor tissue and consumed by the tissue at right mu, and by also the proliferative cells at the right mu c. The oxygen diffusion equation can be written as follow, where P is the density of the proliferative cells, and we suppose that outside the tumor we have C equals C0, a quantity of oxygen on the free boundary. Inside the tumor, the cells move at the velocity v, or by the velocity v, and the conservation law for each cell density is writing as follow. We have the three equations for the proliferative cells, necrotic cells, and the healthy one, which are completed by the boundary condition. The cells are considered being incompressible, and we can suppose that at every point the total quantity of mass is conserved, and we have the sum, we can suppose the sum constant, and we suppose that this constant is equals to 1. We assume that the tissue has the structure of porous medium, and then we can use Darcy law, and we can close the PDE system, because in this system we have the velocity v, and we have to compute it. And using the Darcy law, we have a fourth equation in order to close the system, the PDE system, and P is the pressure in the tumor tissue. And we can, using this three equation, and using the quantity, that the fact that the quantity of mass is conserved and equals to 1, and by adding the three equation, we obtain the new Laplace equation, which permits to compute the pressure P. And obtaining P, we can compute the velocity V. And then we have the PDE model, which is this one, a Laplace equation which can which permit to compute the pressure P, and the third other equation which permits to compute the proliferative density, the necrotic density of cells, or density of necrotic cells, and the oxygen quantity. And we have, of course, the boundary condition. Okay, but what we don't have is omega. Omega isn't a fixed domain. Omega evolves in time, and we have to compute the boundary of omega at each time. And then we have to simulate the evolution of the free boundary. Okay, we suppose that the pressure outside the tumor is equals to P0, the same pressure. We can compute inside the tumor the pressure using a Laplace equation, and we have another boundary condition on the boundary of omega, which is P equals to P0. And then we can define a functional, which is G of omega equals to the integral on the boundary using the goal is to minimize P minus P0. But the computation of the derivative using this expression on the boundary can cause some instability. And in order to avoid this instability, we can use another functional which are defined on d minus omega, on a domain d minus omega. And then in order to compute the free boundary and to compute, of course, all the density which we can search in, which we are searching for, we will use a level set method, and we initialize the location of the tumor boundary, which is given by psi at the time t equals to 0, and then we can solve all the equation in the first domain, but the shape for the shape evolution, we have to use the level set function psi, and the psi equals to 0 is the free boundary at the time t. And by differentiating in t, we obtain the transport equation, which we permit to compute the psi. But we have to compute the velocity v. In order to do that, we can use two approaches. We can use the Darcy law, and the tumor deformation is due to the cells moving during their proliferation, and using the Darcy law, we have the velocity equals minus the gradient of P, and it is easy to compute. We can also use a shape optimization method, which is an optimization problem, and we can compute V by a Lagrangian method, and we can minimize G over omega, as defined by P, but P is subject to the PDE equation system, of course, with a boundary condition. And we have some computation to do using the Lagrangian L, which is defined by the functional G, and by adding all this equation multiplying by the Lagrangian multiplicator and the variational formulation of the PDE system. And then we obtain the Lagrangian.
Okay, alhamdulillah.
Excuse me.
And by deriving L with respect to the state variables and writing the optimality condition, we obtain the equations used to calculate the adjoint state. We have to derive with respect to the pressure, with respect to the proliferative density, and with respect to all the state variables. And then we obtain 4 equations which permits to compute all the adjoint variable phi p and phi p and phi c, etc. The phi e represent the adjoint state variables computed from the Lagrangian associated to the optimization problem. And then we can define the direction of descent, and we can, of course, compute and simulate the evolution of the free boundary. And then we obtain the next algorithm. We initialize the level set psi, and then we can compute all the variables in the first domain omega, pressure and all the density of the cells.
Rajae, there is someone who wants to ask a question.
Okay.
Hadi?
Thank you, Nabil. Just a little question about the minimization problem.
Yes.
The variable is the domain omega?
The domain omega, and also all the density variables and the pressure also.
But omega evolves in which set?
In D. I will show you.
This is
Okay.
this slide.
Omega is inside the domain D, and omega evolves inside D. If we suppose that omega is a tumor, for example, in some organ, D is the organ and omega is the tumor. Okay?
And what is the shape of omega? Because
the shape of omega is unknown, but we suppose an initial location, and then we have to simulate the evolution, supposing that we have some location in order to begin our computation.
And why did you suppose that D is rectangular?
No, we can suppose another form.
Okay.
Is only for simplicity.
The most simple shape is the circular form. I know, but anyway, okay.
This not will have any change in the formulation of the problem and in the resolution.
Because in rectangular form you have 4 vertices, so corner point. Okay.
Yes, but we use finite difference. No, for the first part we use the finite element method, and we have.
Okay, okay, I understand. Thank you.
Okay.
Thank you very much.
Okay, and tumor boundary evolves over time, of course, with normal velocity. This velocity, as I said, can be computed by Darcy law or by the use of the adjoint state. And then we can initialize a cost function and we can compute a first advection velocity. And then we iterate in time and in minimization boucle. Loop, yeah. Okay. And of course, for the second method, it's we have more computation to do because we have to solve the adjoint problem each iteration. And then for using FreeFEM, we obtain this evolution of the tumor of the free boundary. For the first numerical result are down with using Darcy law, and the second are obtained using shape optimization method. We remark slight tumor volume evolution using the first method, but with the second method, we have a spherical shape, which is it is greater than the first results. But about CPU time, using the first method, we have only 17 seconds of CPU time, and using 60 seconds of CPU time for the second method. Of course, the second method use adjoint variables, and we have to do more and more computation. Okay, it was the first part of this talk. In the second part, I will present a hybrid model, which is a microscopic modeling at a cellular level. Each cell is represented by a patch and is in relation with the other agents and with its environment. The behavior of the agents is governed by a set or a finite set of rules deriving from biological condition that describe the phenomena. We will to use the agent-based modeling to describe the cell's behavior and also a PDE equation to compute the oxygen. In this work, we suppose that the environment of the cells have only one nutrient, as in the first part, which is the oxygen. For the resolution, we used NetLogo, which is a programming language and modeling environments for agent-based systems. And of course, we used MATLAB to solve the oxygen diffusion equation. We consider, as in the first part, only the three types of cells: the healthy, the proliferative, and the quiescent one. And we consider some parameters, which are the initial number of cells, the running time of the simulation, mitosis rate, and mutation probability. In NetLogo, the environment is omega. We consider n healthy cells and an initial oxygen concentration in each cells in each patch. The patch can be a set of some cells. And a selection of some patch, which is denoted here by patch S, will act as a blood vessel and will supply the environment with oxygen. And using net logo, we assume that in each time iteration, the environment is supplied with oxygen from the vascular system through the patch S, and this oxygen in the patch S is increased by some quantity, say, external oxygen, which are given by the organ or by the organism. For each cell, if we have the mitosis condition, a cell creates another one. If we have the mutation condition, we have the mutation of the considered cell into a cancerous one. And if the quantity of oxygen is less than the, say, threshold or say minimum, a healthy cell dies, a cancer cell becomes quiescent, and a quiescent cell dies if the quiescence state exceeds the maximum of time. And then the quantity of the oxygen oxygen concentration decrease because a part of it, this quantity was used by the cells. The oxygen concentration are collected from the patch and sent to MATLAB, and we solve the oxygen diffusion equation in order to compute the new concentration using finite difference method. And the new oxygen concentration levels are at the time T plus 1 and are sent by net logo and distributed to the patches. And then we obtain these results. First of all, we have only the healthy cells, which is the first population or the initial population. And then we have the emergence of the proliferating cells in the second figure. As the total number of cells increase, the background color of the patch began to darken because the oxygen level decrease, and black quiescent cells appear in the patches where the oxygen level is low. The patch S, which is the vessel supplying the tumor with the oxygen, is clearly visible due to its white background, and the quiescent cells die and are removed after being deprived of oxygen for a long period. Cancer cells are around the oxygen vessel or the oxygen source to survive and multiply.
what is the period of time between each configuration?
The time I have not don't have here the, but I can see after.
Just an idea. It's about seconds or days or months or the evolution
in the real situation. Of course, is days and month, but in the simulation, it can be some minutes, some seconds, or some minutes.
Okay.
In the next part, or in the last part, I will talk about some sensitivity analysis with respect to some parameters. For each parameter, we consider three different scenarios. And the parameter of interest vary from one scenario to another, but the other are supposed to be unchanged. And each scenario represents the summary of 20 identical simulations. The first parameter is the initial number of cells. We suppose only 700 cells and 1,000 cells and 2,000 cells. By increasing the initial number of cells, the decay of the oxygen supply in each patch is faster. The necrosis of quiescent cells occur at an early stage of the simulation. The tumor is faster to develop around the remaining source of oxygen. It is, as we intuitive results, because if we have in the initial population more cells, more cells will be diseased, and we see the quiescent appearance and the deaths are more faster. The second parameter is the running time of the simulation. By increasing the running time of the simulation, we consider only 200 iterations, 300 and 400, and we remark that the surface area occupied by the tumor increase as well, and the final number of cells does not vary as much. The third parameter is the mitosis rates, which control how fast the cell can divide. And the cells divide more and the tumor cell number increase with lambda S, and the tumor surface area decrease in the same proportion. With a large number of cells, the competition for the oxygen source becomes stronger. The cells cluster around the oxygen vessel and shape a thicker tumor, which causes the tumor volume to shrink. And we remark that the surface of the tumor is less than the first for when lambda S increase, but the density is greater. The last parameter is the mutation probability, which controls the inclination of the healthy cells which mutate into cancer cells, and by neglecting the mitosis, the tumor surface area decrease and the total cell number doesn't vary, but the cell distribution among the different cell types differ from a scenario to another. As the number of proliferating cells increase in the tumor, the cells tend to be around the oxygen source, and causes that the surface occupied by the tumor decrease, but the tumor density increase. And we have this simulation. We remark that in the first diagram, some healthy cells, which are, and in the second we have less, the number of healthy cells is less than the first, and in the last one we have only the cancerous cells, but we have of course the vessel who supply the cells on oxygen. Before to conclude, I would like to show you a video of the simulation using NetLogo. Okay. In this work, we used the two approaches. The first one using PDE systems or PDE equations. And in the second one, we used multi-agent simulation, but using also PDE equation, which is an hybrid model. The both developed model can be extended to take into account the effects of medical treatment on the tumor development, which is work in progress now. We remark that the continuous model is based on abstract and mathematical approach, but the second approach, combining the oxygen diffusion and the agent-based model, is more easy to simulate by the clinician. Okay, and thank you very much for your attention. Here, vous avez, you are some used references.
Okay, thank you, Rajae. Thank you for this very beautiful talk. It's very beautiful and impressive results. And is there some questions? No questions?
I have two questions.
Okay, please, Hedi.
Thank you. Thank you, Prof. Raja, for your presentation. The first question is physical and the second is mathematical. So to measure the relevance, la pertinence in French, the relevance of your mathematical model, did you compare the numerical result with reality? Okay, this is my first question. And my mathematical question is about your PDE what did do you have any result on the uniqueness of the result before doing or achieving the numerical computation? Do you have any result about the uniqueness?
Okay, thank you for your question. About the comparison, we compared only the first approach with some results in the literature, but with the reality, it is our hope. We are collaborating with some oncologists from University Mohammed VI University. From Mohammed VI University, and there are some oncologists, in particular Dr. Nabil Ismaili, which is our collaborator in this work, and we are working on some practical cases, and we have some can I speak in French, Nabil?
No, please, because there is a lot of English speaker with us.
Okay.
I'm sorry. I'm really sorry.
Okay, okay. I will try.
But you can tell it in if you can translate perhaps some short. If you miss some words or.
Okay.
Okay.
We are collaborating with a professor from Mohammed VI University. And he give us some the dossier.
Yes, some projects, some.
Des dossiers de malades, des dossiers de personnes malades.
Folder.
Hey.
Folder.
Okay, we have some data from the hospital.
Folder, yeah.
Yeah, and we have to use image treatment and some other methods in order to compare and in order to achieve these parts. And I think we have with us now Benmir Mohammed, which is working with us, and Selma Shabar, and other young researchers working in this project, in order to have some proof of this comparison. Because in order to compare, we have to obtain the real evolution of the tumor. This evolution, we can't have the evolution of someone which is deceased. He used treatment, but in this first part of the work, we suppose only the oxygen, and the work what Benmir will do is to consider the treatment, and considering the treatment, we can compare with some data of some person who had cancer.
And how do you include the treatment in your equations?
We can do that by considering another equation who diffuse the treatment, but perhaps it is not the same like this equation. We have to search, and we have to modelize the diffusion of the treatment.
Okay.
And we will have another equation. About your mathematical question, there are some classical equation. I think there are not difficulty in the proof of the existence of the solution, but the difficulty is, of course, in the computation of the derivative, we have to prove the existence of this derivative in some space. And I think it is possible because we proved the same results for another problem before.
Okay.
Okay, thank you.
Thank you.
Rajae, when you showed the two shapes of in your results, and you calculate these shapes by two different methods, you find the circular shapes.
Yeah.
And the second is an irregular shape. Yes.
Yeah.
And how do you know that the circular is better?
We don't know anything. we are waiting for the real results in order to compare. Okay. But for using the first approach, we remark that the tumor is plus petite.
Smaller.
It's smaller, yes. It's smaller than the second. And intuitively, if we don't use any treatment, the tumor have to be greater.
Okay, there is no reason to minimize. Okay.
And in comparison with some classic, with some results from the literature, we remark that is the next evolution. Is the second evolution. But we have we can't be sure.
Okay. And the software NetLogo is okay.
Is a free software.
Okay.
Used for
agent-based system. Okay.
Yeah. For agent-based system, but for different system in finance, in economics, in biology, and very different systems. And in our laboratory, we used it in the first time for the financial engineering, for the financial problems.
Okay. Okay, it's very beautiful. Thank you very much, Rajae.
Thank you for you.
Is there other questions, please?
Yeah.
Do you have other questions?
Yeah, please. I have one, Nabil.
Okay.
Thank you first for the talk. Nice talk.
Makrama.
Yes.
Okay.
Yeah. Thank you, Nabil. Yeah. So my question is a simple question. Why you take the diffusion equal to 1 since you consider, I think, oxygen diffusion, right?
No, not the diffusion equation. We consider, okay, one moment.
I mean the viscosity of the diffusion, of course, in front of the diffusion term.
Is the sum of is the quantity of mass, because the cells are considered to be incompressible, and we can suppose that the sum is constant, and we can use 1 because not change anything in the resolution. Because it is only the incompressibility condition.
Yes. So there is no viscosity in this in front of this Laplacian of C, right?
No. Because
problem of scaling 1 or any other value.
Yeah.
No, but scaling, if it is too small, then you will have maybe some problems in numerical simulation, I think.
If we sum the 3 equations, we have the derivative equals to 0, and we have for the Laplacian you mean?
Yeah. Yeah.
Okay, the Laplacian is obtained from the addition of these three equations. When we add the three equations, we have the derivative equals to 0, and we obtain the divergence of V, and the divergence of V of Darcy law will permit to obtain the Laplace equation.
Okay.
Okay.
Okay, thank you.
There is another question, I think. Mr. Gobina, you have a question?
Hello.
Yes.
Yes. Yes, I wish to ask if V must be positive or can it be negative?
What?
If V, the diffusion velocity for the plurificate, if it can be negative or positive.